All right, so this is going to go through the life cycle of a star. We're going to focus mainly on a star like our sun. Um, but we talked about the formation of the universe. Now we're going to focus in on the formation of stars and what that looks like. Now, important that the fate of a star, basically how it goes in its life, like what path it takes in its life, is 100% dependent upon the mass of the star. So you're going to write that down. The mass is what determines what the star becomes. And so when we reference things, when you see this throughout this MO, that's going to be the mass of our sun. We compare a lot of, usually in astronomy, they compare just to have a reference point. Like, hey, compared to the mass of our sun, this is how big or small, more massive the star is. All right, so all stars are going to start out as a nebula. And these are just some pictures of nebula. Basically, it's a cold, dark interstellar cloud of gas and dust. All right, but what happens is that there's a gravitational attraction that's going to start to pull them together. All right, this gravitational attraction is going to pull them together. This is the beginning formation of a star. All right, so in the nebula in your notes, you just put nebula. It's a cold, dark cloud that is being pulled together by gravity. All right. A protostar, then, what happens is that as they get closer together, and this is a lot here, but if you think of it like in terms of human development, the nebula is like, hey, we're thinking about having a baby, and then the protostar stage would be, we're pregnant, and so this is where the star is starting to form. It's not quite a star yet, but it's starting to develop. All right, it's starting to get there. It's starting to take the shape and starting to get there, almost a star. All right, so this is the embryonic stage of a star. All right, and basically what's happening is that it's continually collapsing. This nebula is continually collapsing due to gravity with the increased mass as density is increasing. Higher amount of mass in a smaller amount of space. The gas pressure increases. As the gas pressure increases, that causes the energy of the particles to move faster. When something has higher pressure, the kinetic energy moves faster. You're going to have more collisions between particles. As the kinetic energy goes faster, the temperature increases, because we've already learned that temperature is kinetic energy. And so basically a protostar is where the gravity is pulling them close enough together to where the temperature is starting to increase. The pressure is increasing, the temperature is increasing. And eventually it's going to get to a point where the gravity is going to pull it so tight together, the pressure and the temperature is going to be moving at such a high rate that it's going to get hot enough to form nuclear fusion. Okay, so protostar is just where it's coming closer and closer together. Kinetic energy increasing the potential, the kinetic energy increasing the temperature, and eventually it's going to get to a point where the pressure increases the temperature so much that fusion will occur. Now, I'm going to skip to fusion real quick. We've already talked about this. We talked about this in the last unit. But remember, fusion is when the nuclei join together. All right, it's when and it takes a tremendous amount of energy. All right, and so you have these atoms, these hydrogen atoms. Once again, they repel each other. A typical hydrogen atom is just a proton. You can have a proton and a neutron, but basically they repel each other. But if they're moving fast enough, you can get them to overcome their repulsion, and then the strong nuclear force takes over and they smash in and they form a nucleus of an atom that is much stronger than the repulsive force, but it's only really strong at a very, very short distance. All right, and so that is the fuel. All right, nuclear fusion, just to recap that, nuclear fusion is the fuel that makes a star born. All right, and so nuclear fusion is the fuel that makes a star born. And that's when it becomes a main sequence. So once again, sticking to the human side, if nebula, it's like, oh yeah, we want to have a baby protostar, we're pregnant, yay. Main sequence star, that's the next phase. So your main sequence, that is basically from when you're born up until you're like 70 years old. All right. So a star, even though I'm going to go through these like they're all equal amounts of time, a star is on its main sequence virtually its entire life. All right. So basically, what has to happen for a main sequence? One, and I want you can write this down. Fusion must occur. The temperature must be high enough for fusion to occur. All right, because that's what gives the star its fuel. That's what bursts the star. But then the other part, there's two parts to main sequence that you're going to have to write down, is that there has to be an equilibrium established. All right, what I mean by that is the outward pressure caused by heat, from the fusion, and the inward pulling of gravity, those have to equal each other out. All right, so it's going to continue to collapse until these forces are equal. All right, so the pressure from fusion outward, the inward pressure of gravity. Gravity's trying to bring everything together. Fusion is causing everything to go out. Once those forces get balanced, all right, then once again, main sequence. The star is now in equilibrium. It will continue this process for most of its life. It's going to be fusing hydrogen for most of its life. All right, and the stage is the main sequence. That's the stage our sun is currently in. All right, and typically much larger massive stars, they will reach higher temperatures faster. They'll burn their hydrogen much faster. They'll glow brighter, but they do have shorter lifespans. Right? So, and this is just a picture of what we're talking about. So, inward pressure of gravity. Gravity's trying to bring everything together. Remember, gravity is that attractive force between all objects. Pressure from the fusion is pushing outward. Once that becomes balanced, once those arrows are equal, all right, that's the main sequence. All right, so then the next part, once again, I'm going through this quick. It makes it seem like, it's all the same. The next phase is a red giant. All right, now this is a very large star, high luminosity, very low surface temperature. But basically what happens is that all the hydrogen, this is the next phase. This is like time to take grandma to the nursing home kind of phase. All right, so this is where there's no more hydrogen left in the core. All right, there's no longer hydrogen remaining in the core to fuel the nuclear fusion. And so what happens is that it will balloon up. The temperature of the star will drop. It's going to glow red, but fusion stops in the core. The core will contract, and to keep that equilibrium, it'll send its outer layers out. It'll grow significantly. And basically what's going to happen is that, let me find it, there it is. Nuclear reactions in the core are going to be helium then in the core is going to start fusing into carbon. All right, so helium will start fusing into carbon. So basically in a red giant, what you need to put is that there's no more hydrogen in the core to fuel it. It starts to burn helium into carbon. And to keep the equilibrium, it basically sheds its out. The outer layers expand significantly, becomes significantly bigger, and then eventually what's going to happen is that once this is a much shorter phase of its life, it's going to eventually be left with a remaining core and turn into a white dwarf. All right, and so like for our sun's going to become a red giant. What would happen is that the sun would become so bloated, its surface would reach the orbit of the Earth. All right, you think how far away we are from the sun? That's how massive it's going to balloon up. Essentially, once that happens, the Earth obviously is going to be uninhabitable. Good news is we'll be dead. The sun will become so bright, so big, our atmosphere will evaporate, the oceans will boil off, and the surface and dirt will melt into glass. Whoop. Right. And then after that, like I said, after it falls off, after it becomes a red giant, it's going to become a white dwarf. Once the core of the star begins to exhaust its reserves of hydrogen, the star quickly becomes unstable. It will evolve from its state of equilibrium because the star no longer is able to create outward pressure. Gravity is unopposed. So since the fusion is no longer occurring, I shouldn't have said hydrogen, but as the fusion is no longer occurring, gravity is just going to pull it in. The star will shrink into a white dwarf. It's extremely dense, but basically it's no longer fusing. It's really bright because it's really hot. It's really hot, but it is dead at this point. So this is really the death of a star. And so a star like our sun, what will happen is it'll become from a nebula to a protostar. It's getting there, and then once it's birthed, it's going to stay on this process for a long time, become a red giant, and then eventually that will collapse in on itself, create a nebula, and then you'll be left with a white dwarf. Now you can see with large stars what happens, because I said the mass of a star, more massive stars will have a different lifespan than our sun. So when they're more massive, what will happen is they will become a supergiant. And depending on how much more massive they are, when the supernova occurs, they will either create a neutron star or they will create a black hole. All right, really, really, really massive stars create black holes. All right, and so a supergiant is when it's stars that are about 8 times the mass of our sun. They become a supergiant. Like I said, it's like a giant but bigger. All right. High enough pressure and temperature to fuse elements even heavier than carbon. All right, so where you get things like eventually iron will start to they'll eventually get to fusing things like iron, and then iron can't fuse anymore. So once that happens, that's when you're going to get rebounds off solid iron core, produces a shockwave. This explosion is called a supernova. All right, the brightness of it, once again, the outer layers are blasted into space, blast its guts out into space. That's what it talks about. And so it burns. It's really, really bright. Here's a picture before and after of a supernova. All right, and then it's left is a neutron star, extremely dense. It's like about the size of, like, if you think of like New York City, it's like the size of New York City, but it is the density of, I don't know if it's on here, I don't remember. I mean, it's like way more dense than our sun, and it's significantly, I mean, it's like a million Kelvin compared to our sun. All right, it's extremely high temperatures, extremely dense. They talked about in the video we watched on Friday that a sliver of it is would weigh as much, just a small grain of it would weigh as much as a pyramid in Egypt. All right, it's so massive. And then really massive stars become black holes where gravity overwhelms itself, and it's so dense not even light can escape. Right. And so that's the path of, that is the formation of stars. More dense, I can't pause this. More dense stars will become supernovas, either neutron stars or black holes, or more massive stars. Stars like our sun will become red giants, and then white dwarfs.